Thank you so much. So thank you so much for coming to the POPL 2023 student research competition. So each presenter will have 15 minutes. So we are in a short schedule. So I'm going to go right away. The first talk is going to be scalable synthesis of regular expressions from only positive examples by Mark and Elizaveta.
Okay. Hi. So I'm Lisa. This is Mark. We're from UCSD. We're undergrads, and we're very fortunate to be advised by Professor Policarpova and Professor Burkett-Patrick. And today we're going to be telling you about synthesis from only positive examples. So let's start. Why do we even care about this problem? So imagine you're a data scientist and you're working for a very large company and you kind of hate your job and your boss gives you a really large text file and asks you to find Brazilian CMPJs in the large text file. So first you're like, what are Brazilian CMPJs? They're Brazilian company identification numbers. And you can quickly find two positive examples in the file, but you don't really know the space. You just find out what Brazilian CMPJs are. And so it can be really difficult for you to come up with negative examples, and also with a natural language description of the problem. And so in an ideal world, you would input your positive examples into a synthesizer and get a regular expression. But prior to our work, Regex Plus, there existed no synthesizer that could do that. But now, take your two examples, put them into Regex Plus, and boom, you get the correct regular expression for Brazilian CMPJs.
So what are the challenges here? So right off the bat, the first challenge is that the problem is vastly underspecified. Like in terms of cold hard spec, the only concrete thing your output has to do is it has to be a regular expression that matches the inputs. And so here's a regular expression, all text. That's not helpful because it doesn't capture the domain. So it's too general, which syntactically it's too simple. And so you might be like, well, then just get the most specific one, right? But you could say this example or that example. It's way too specific. It also doesn't capture the domain and also is not helpful to the end user. And so you need to strike this balance between simplicity and specificity and find some way to like define what even is the best regular expression. And this is sort of a wishy-washy human concept of what the best thing is. So you'd also want some like human data about people. And of course, it's a synthesis problem. Search is hard. So first we'll address what is the right answer. So we have developed a pragmatic ranking function that we use that's based on Bayes' rule, and it's used to define to compare two regular expressions to see which is better. And so using Bayes' rule, we want the regular expression that was most likely given these inputs, and we can compute this in terms of the two factors with up to a constant of proportionality. One of the factors is the probability of the regex from a probabilistic grammar, and this naturally is bigger when you have a simpler regex. And so this biases it towards, this naturally incorporates the simplicity aspect of the problem, of the specification. And the other factor is bigger when it more tightly matches the inputs. So this naturally incorporates the aspect of specificity to the examples. So thus, using Bayes' rule, we're able to incorporate both simplicity and specificity in a principled way. And the other great thing about this ranking function is that it's compositional in such a way that we'll be able to use it to compute edge weights later, which will be great.
So we have this great ranking function, right, that we tell you that it works. But does it actually work? Does it actually capture how humans think about regular expressions? And so to solve that, we run a human study, which we pose as a game because we believe that helps us users understand what we're trying to get them to do. And so we pretty much give them regular expression and then ask them to describe it using only positive examples. We have some aliens to make it more fun. But overall, we collect 412 new data points, and we use these as our evaluation benchmarks. Because prior to our human study, there was not really any corpus of benchmarks for only positive examples, since if you search Stack Overflow, there's going to be natural language descriptions most likely, since the user would have written it out. And so we hope to, and additionally, we will use these for evaluation, as I mentioned previously. And our evaluation does show that the pragmatic ranking function we showed you earlier mostly captures how humans think about this problem. And so that brings me to our second contribution, search algorithms. So I will present 3 different search algorithms that we developed for this problem and kind of talk about the pros and cons of all 3. And so to do that, we're going to use a walkthrough example to illustrate the differences. And so let's say you're trying to synthesize a regular expression of digit plus followed by 0.5. So kind of some rounding of digits. And so you could think that 2 examples that could describe this regular expression are 2.5 and 10.5. So that brings us to our first problem. How do we represent all of the possible regular expressions that would describe these 2 input examples? And so our first method is based on version space algebras, which are common data structures used for synthesis. And so in this graph, our nodes are amount of characters parsed from each of the examples. So as you go to the right, you will be parsing from 10.5, and as you go down, you'll be parsing from 2.5. And the correct solution will have to reach the bottom right corner from the top left corner. And so what are the edges in this graph? The edges are atomic regular expression components. And as you can see, there are a lot. We're actually not showing all of them because this will just be too difficult to see. But we have compactly represented our space, which is great. And then we can give the edges weights based on the pragmatic ranking function that we have. And so then finding the best regular expression simply becomes finding the best path in a DAG, which is amazing. However, one issue is this is only 2 positive examples, and they're very small. So when we add more examples, this graph blows up exponentially. With 3 examples, it becomes 3D, and it just gets really complicated. So while this does have completeness guarantees, it is very slow and is not very scalable. And so we propose a second search, which is beam search. So beam search is a popular approximate algorithm used in machine learning. And the way it works is that you create certain buckets to divide your search space and then take top K from each of the buckets. So the biggest problem with beam search is how do you create these buckets? How do you divide your search space in a way that while you're approximating, you're still able to get one of the best solutions or the optimal solution? So here our contribution is that we decided to divide our search space based on the amount of characters parsed from each of the examples. So starting at 0 characters parsed, going to 1, and then to 7, which is total number of characters in our 2 examples. And then at each bucket, we take top K. So for this example, we'll only take 2. And then the search looks something like this. And as you can see, it is really fast. We do not build the whole DAG. And so as a result, we're able to quickly find the solution, but we do lose the optimality guarantees. And what I mean by that is that while our solution is still sound, meaning it accepts the inputs, we no longer can guarantee that it's optimal given our heuristic that we defined earlier. And so that brings us to A star.
So in order to still have an efficient search algorithm that retains the guarantee of giving you the actual optimal regular expression defined by the ranking function, we employed A star using an admissible A star heuristic. And so A star likewise only explores a fraction of the edges. But of course, to employ A star, you need to be able to soundly under-approximate the score of what's to come. And so for that, we have our admissible heuristic. So the score of what's to come is given by this formula, and then we want to bound it below by something else. And so we bound it below by this other formula, which we can calculate efficiently by considering subproblems with subsets of the examples. So if your problem has 5 examples, you could consider the subproblems for like each pair of examples, which are easily solvable because the graph is a lot smaller, and then use those subproblems to bound below the score and get an efficient A star heuristic. So lastly, we want to show you how it works, or how well it works. So this first graph is going to convince you that our ranking function does well. On the left, we have this left column is a purely enumerative baseline from the literature. A common technique in synthesis is simplest first enumeration, where you enumerate programs and take the simplest one that works, given the examples. And the idea being that the simplest program that replicates the desired behavior is likely to be the one that succeeds, that is desired. But for our domain of, this doesn't work out so great because the simplest one, it will be overly general. And so the green bar at the bottom that's very small represents how often that matched the ground truth regular expression, which was less than 5% of the time. On the other hand, with our pragmatic ranking function, we're able to find the ground truth correct regex over a third of the time. Another thing that you'll note is the yellow bars show how often it times out or runs out of, or how often it doesn't time out and doesn't run out of memory. So the beam search bar is a lot higher than using VSAs or even A star on the VSA. And interestingly, the beam search green bar is also higher, just because although it doesn't guarantee the optimal result, it's still good enough of the time that solving more of them before the timeout lets it succeed more often. And if we had let A star run for eternity, it would also have as high or higher of a green bar, but we didn't have that time, unfortunately. This next graph will convince you that our search is fast. So on the x-axis, we have the amount of time taken by the standard VSA-based algorithm. And on the y-axis, we have the amount of time taken by the A star on the VSA. And so if the points are below the line, then it means the A star is faster. Another thing that I want to point out very quickly before going on to the next slide is that you'll notice that the enumerative baseline gives answers for all the problems. And however, like subjectively, those answers are tend to be a lot worse or more overly in the way of being overly general than the answers that our tool gives, even when the answer that our tool gives doesn't exactly match on the nose the ground truth spec.
Kind of bouncing off of what Mark just said, we can truly see this in the examples. But first, let's look at something that we get correct. So the user was given this regular expression and then asked to come up with some examples to describe it. And they came up with this. So it was their choice to outline 5 examples. And I think this actually captures the spec pretty well, in my opinion. And so then our competition, RegLPB, came up with this regular expression. So as you can see, it does fit the spec, but I would argue that it's not super helpful to the user, just because the only thing it says is that it has to start with a digit. And then so VSA runs out of memory because it is a lot of examples and they're really long. But then both A star and Beam gets the correct answer. So go us. Now, what about the times when we don't actually match the spec? So here the user was given this regular expression to describe, and they came up with only 2 examples. So I don't know if I could synthesize the regular expression from this, but maybe someone can. So RegLPB comes up with this. So it has to start with C, and then anything can happen. Okay, fair. So we come up with C, and then it has to be followed by a digit plus. So I believe that this is kind of describes the spec a little better, just because we do kind of constrain the everything to digit plus. And anecdotally, we report in times when we are wrong. It's kind of a similar idea where we do fit the spec, but maybe we don't fit the spec 100%. And further, to illustrate this, if we augment this like example set by just one more example, we're able to get it right. And I think this is really important because it shows just how powerful our pragmatic ranking function is. Because by repeating more of C0 plus, or C0, we're able to see that that's actually what the user intended. And so it kind of shows how we capture more information with more examples given, while RegLPB still outputs the same exact example, no matter how many more examples the user provided. And so main takeaways from our talk. 1, we think that our talk really shows that one-shot synthesis from just positive examples is possible. So yes, the search space is really big and ambiguous, but using our techniques, which I believe can be adapted to other domains, this is a problem that could potentially be solved in the future. And then another thing, Regex Plus is great. You should all use it if you're searching for regular expressions. And that's it. If you have any questions, thank you so much for listening.
So we will have 1 quick questions, and in the meantime, I wish the next presenter will set up the devices. Questions? Yep.
Could you comment on the possible relationship with something like flash fill? which is, of course, the poster child for synthesis techniques with these kind of numbers and things like that, and how your framework might interact with something like that.
Right. So Flashfill also uses. Should I use the mic? So Flashfill also uses VSA-based techniques, and they're as we do. They also have a very complicated ranking function. If I remember right, I think they like have some giant neural network that they trained on a bunch of stuff to say what the answer is. So here we have some stats. We do like probabilities, and it works out great. So this is that's a main difference. I don't know. Yes, I hope that answers your question.
I'm sorry, I think we should stop here to continue to the next schedule. I'm sorry about that. And yep.